Hello and welcome to this Isaac Physics online tutorial. Today we'll be covering some extra material from an exponential workshop. This is so mostly for people who have attended the workshop. There are many across the country organized periodically. There was one last week. There's going to be others soon. So this might not make too much sense for you if you haven't seen the material in the workshop and attempted it during the workshop, as we will be going through the more advanced problems today. However, please stay tuned with the events page on Isaac Physics, where you can see all sorts of either online or face-to-face events which we run all over the country for your own benefit. Okay, so one important thing to note is that you should really log in with your Isaac Physics account if you have one, in order to benefit by the possibility of sending me questions in real time. So I'll be checking them periodically as I explain things here. I've already received a few questions from you, so thank you very much for those. So please do ask questions, because chances are that I'm not being clear or I slipped somewhere, and it would be great if you could correct me for me, for yourself, and all your peers. Okay, so let's begin. I received a few questions for about almost all, in fact, the questions in the worksheet, which is great. In particular, let me just address very quickly one question I had about the nuclear chain reaction question. So it's just that we have been perhaps a bit sloppy in the wording of part D. So part D of the nuclear chain reactions question states, neutrons are also lost at a rate R1 due to absorption by non-splitting nuclei. Okay, and I think one of you correctly wasn't quite sure what was meant by this rate R1. And in other words, you weren't sure whether this meant you had to add the term R1 times n being the number density of neutrons, or if you just had to add the term R1. Okay, so the correct answer is you should have added the term R1 times n in your differential equation. And really what this text should have said is a rate per neutron, if you like, of R1. Okay, so the person who asked the question about this, you did the calculations correctly and you interpreted the question well, and it should have been worded slightly different. Thank you very much for pointing that out. Okay, so let me go now to the again note in response to one of you something about the leaky tank question. You asked what the solution for the equilibrium height was, and your answer was R over PG. However, it seems that you're missing a factor of A. So the point is, and let me just share screen so you can all see this. The point is that in this question, which I'll read again, so a cylindrical tank of cross-sectional area A filled with liquid to an initial height of h0 has a small hole in its base. Fluid leaks out at a volume flow rate I, where I equals AP, with P the pressure difference between the fluid at the bottom of the tank and the outside, and A is a constant. The hydrostatic pressure difference, which is called P, depends on the depth of the fluid. Okay, so we're being told that P equals rho GH, where rho is the fluid density, G is the acceleration due to gravity, and H of T is the current height of liquid in the tank at time T. Okay, so as usual, we draw a picture of what's going on. This is possibly the single key, most important thing to do at the beginning of a question, and also to write down what we know. Okay, so here's our tank. It has a cylindrical base, or rather it is cylindrical. has a circular base. Here's the top of the tank. And let's say the water is up to this level. Okay, of time t. The area at the bottom is A. So this is the area. And there's a hole, say here. Okay, and then this height is what is being called h of t at the time t. Okay, so we're being told, and let me answer the first part of the question. Find how h of t varies as the tank empties. Okay, so we're being told in the question that fluid leaks out at the volume flow rate I, where I equals AP. Okay, so the I equals AP, but what is I? It is the volume flow rate. Okay, what does that mean? It's a rate at which the volume of fluid is lost. Okay, so it is a volume per unit time. It's a change in volume, in fact, per unit time. So it's something like dV by dt. Okay, a little change in volume over a little change in time. However, we need to bear in mind that the volume of water is suddenly decreasing. We know this physically. And therefore dV by dt would be a negative quantity. So if we want I to stay a positive quantity, such as A times P, then we need to put a minus sign by hand. Okay. All right, so the next step is to remember that the volume, that is not the volume of the entire container, but the volume of the water that hasn't yet leaked out, okay, that's remained in the container, is given by V equals A times H, and H of course is a function of time. So V also is a function of time itself. This means, so combining the first equation star and the second equation double star, this means that AP, or if you like, let's put the minus sign on the right of the equation in star. So minus AP equals dV by dt. And that equals, well, A is fixed. It's just a cross-sectional area of the cylinder. So that doesn't change with time. So when we take the derivative with respect to time of A times H, we just end up with, we can pull the A out, and we end up with A dH by dt. Okay, so we're nearly there. There's another piece of information that I need to remember from the question, because I'm being told what P is. Okay, P is the hydrostatic pressure, and we're being told that, and I'm going to write it on the top, collecting everything I know, that P is at any point instant of time given by rho times G, these are both constants, times H. H is not a constant. H, of course, decreases the time. Okay, so now let me combine this, this third equation, let me give it 3 stars, with what we already had, the bottom equation, the differential equation which we obtained for dH by dt. Okay, so I end up with A dH by dt equals minus AP equals minus A rho G H of t. Which means we end up with one of the kind of equations which we would have met at the workshop. Okay, this is, I can maybe clean this up so that it looks a bit nicer. It's dH by dt equals minus A rho G over capital A times H of t. Okay, let me put this in brackets, and let me call the quantity in brackets lambda. Okay, so lambda is A rho G over A. So all I've ended up with is an equation of this form. dH by dt equals minus lambda h of t, where lambda is a constant. This is exactly the kind of equation we met at the workshop. And let's get some space again. The solution, if you remember, to an equation like this is that h of t will be given by the initial height h naught times e to the minus lambda t, which means h naught times e to the minus a rho g over n t. Okay, so to address the other section, the part B of the question, we're being told now that fluid is replaced at the rate of r. What does that mean? So this is now the next part of the question. Where we, so originally we had this differential equation, h dh by dt was equal just to minus a rho g h. Okay, this was just because the water is leaking out of the bottom hole, and therefore there's a volume flow rate given precisely by the right-hand side. However, here we're also being told that fluid is replaced, so it's kind of being replenished as it leaks out of the bottom at a rate of r. So all that means is that we have to add an additional term to the right-hand side, plus r. And so this is it. This is really it. This is the new differential equation. The first part of the first subsection, the sub-question in part B asks, what is the equilibrium height of fluid in the tank at long times? Okay, so you can imagine the sort of physical situation. Water is leaking out of the bottom, but it's also being replenished. So you can imagine that there will be, after a long time, a height at which the most convenient sort of thing is for the water level to stay where it is. Okay, so let's be more precise and consider what does it mean for the fluid to have reached an equilibrium height. Well, it means that the height doesn't change with time. So it means that at equilibrium, dH by dt, in other words, the rate of change of height with respect to time, is just 0. Okay, this implies then that at equilibrium, let's call the equilibrium height h ek. Okay, so h ek is the equilibrium height. Then at equilibrium, we must have that 0. Okay, the left-hand side of the differential equation that we wrote must equal to minus a rho g h sub ek for equilibrium plus r, which is a very simple equation to solve for the equilibrium height, and gives us just r over a rho g. So some of you asked about the solution for the equilibrium height, and I think you gave me almost the right answer. You were just missing this a at the bottom, which is this constant, depending on the characteristics of the hole. Okay, so moving on, because we want, I would like to cover the question on the bouncing ball, which is a very interesting question, especially if you are slightly mathematically inclined, but there's also plenty of physics to discuss. So Let's have a look at that. Okay, so reading the question. After a little investigation, it can be shown that the height of a bouncing ball can be expressed as a geometric progression. Okay, and we will see that in a second. Quantities that increase or decrease geometrically are in fact exponential processes. The quantities change in direct proportion to themselves, and some algebraic manipulations can expose the natural exponential form. So we're going to discover all these things in this question. Okay, let's read the preamble. A ball is dropped from an initial height h0 on a table such that the height of the bounce is h1 equals alpha h0. Draw a diagram showing several bounces. Okay, so this is a very good idea to do a diagram of what is going on. So this is my horizontal sort of table, and here is the ball, and it's initially dropped from a height h0. Of course, there's gravity acting downwards, as we know. Okay, so the important piece of information here is that the height of the bounce after, so the maximum height after it's bounced once on the horizontal table is given by alpha times h0. Okay, so it will go down, it will bounce up again to, let's say, somewhere here. Okay, and the piece of information here is that this new height, let's call it h1, is given by alpha h0. And alpha is, of course, let's write it here somewhere. Right here, alpha is, of course, less than 1. Physically, you will never expect the height to bounce even higher than it was before, of course. Okay, and also okay, well, let me read part A, which is using the properties of exponentials and logarithms, show that the height of the nth bounce as a function of n is hn equals h0 e to the cn, and give an expression for the constant c. Reassure yourself that this is a decaying function. Okay, so if h1, first of all, let's think about the subsequent heights. And by the way, I hope this is clear. Sort of time is running to the right in the sense that I'm taking snapshots and sort of putting them to the right of the previous snapshot each time. Okay, so the following height is given by, let's say, an h2. So you perform another bounce and reach a height h2. Well, how is h2 going to be related to the previous h1? Well, it's just going to be the same law that relates h1 to h0. And that law was that a subsequent bounce height is given by the previous bounce height times alpha, this constant. Okay, so and what about h1? h1 is given again by alpha h0. We saw this a second ago. So you end up with alpha times alpha h0, which means alpha squared h0. And okay, for instance, space here. Let me just record here that gravity goes down. You can go on and on, of course. Okay, and ask, well, what is the height at the nth bounce? Okay, let's say the ball is here. Let's call it hn. Okay, so let me write this down below. Well, just by repetition of the exact same reasoning, so we've seen that after one bounce we have alpha, after two bounces we have alpha squared. After n bounces we simply end up with alpha to the n times the original height h0. And okay, so this is it. This is the formula for the height of the nth bounce in terms of the original bounce, the original height. Okay, so now we're being asked to show that the height of the nth bounce as a function of n is given by not only what I just wrote, but also supposedly this should be equal to something like h0 times e to the cn. So is this the case? Can this be done? I guess is the question here. Well, so we want to solve this equation effectively for C and see if this can be done. So we want to solve h naught times alpha to the n equals h naught e to the cn. H naught is not 0, so we can cross it out very easily. And we end up with alpha to the n equals e to the cn. And well, e to the cn is nothing but e to the c to the power of n by the properties of the exponential functions which we discussed in the workshop. So I can get rid of the powers of n on both sides of this equation, linking alpha to the n and e to the c to the n, and end up with just alpha equals e to the c. So if you like, I've taken the nth root of both sides of the equation. Okay, so we know now that alpha equals to c has to be such that e to the c equals alpha. But this is exactly the definition of the natural logarithm, which again we met at the workshop. So this equation can be satisfied if c equals the natural logarithm of alpha. So yes, we can express the height hn as h naught e to the cn if c is equal to, so now I can write it on the right hand side above, is equal to the natural logarithm of alpha. And we'll be asked to reassure ourselves that this is a decaying function. So why is that? Yeah, you might worry that this is e to the something times n, so isn't that going to exponentially increase? Well, is it? C equals the logarithm, the natural logarithm of alpha, and if you remember your sketch of what the natural logarithm looks like, it is something like this. Let's say this is x, and this is the natural logarithm of x. So at x equals 1, the logarithm equals 0, the natural logarithm equals 0. And also for x less than 1, the natural logarithm crucially is negative. So this natural log of alpha is actually a negative number. So you have e times minus a positive number times n. So this is an exponentially decreasing function. So it is in fact describing a decay process. Okay, let's jump to part B. How far does, let me check if there are questions so far. Okay. So someone is asking about questions they submitted yesterday. So I hope I've already answered some of them, and I'm going through the other ones just now. So I'll try my best. Okay. So part B. How far does the ball travel before it stops bouncing in the ideal case? Why might this distance not be attained in practice? Okay. So starting afresh. Let's just record what we had, and what we had was that hn is equal to alpha nh naught, or if you like, h naught e to the ln alpha n. Okay, so how far does the ball travel before it stops bouncing? So if the ball is here at the nth bounce at the height hn, sorry, so if the maximum height before the nth bounce, rather, which is hn minus 1, is this, then sorry, excuse me, this is not what I want to say. I want to in fact first draw the ball at the moment of the nth bounce. So this is the moment of the bounce. Okay, the nth bounce happens exactly here. After this, the ball will travel up, of course, a height given by hn, and then just down again. So again, time flows to the right here. The same height. So the total distance traveled is given just by 2 times hn. So after the nth bounds, and before, of course, the n plus first, this is just equal to 2 times hn. Okay, so this is simple enough. Also, let's not forget about the very beginning of the process. The ball was starting from a height h0. So when we calculate the total distance traveled over the entire process, not just between any two given bounces, we have to not forget about the initial height h0. So what is the total distance traveled? And this, I mean, overall bounces, overall infinitely many bounces, in the ideal case. This is given by h. We can call it h. And okay, so we have h0, that's just the original distance, the initial distance that it has to travel before the first bounce, plus infinitely many terms like this, 2h1, 2h2, plus dot, 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 all the way to infinity. Okay, so we want to somehow calculate this. Let's look at this and see, well, there's a factor of 2 in basically all the terms up to infinity, except for the very first. Well, we can just fix that quite easily by saying that this is just given by 2h0. So let's just pretend there's a 2 in front of the h0 to begin with. But then let's just subtract it off at the end. So we've done nothing interesting, but it is now maybe a bit useful because we know the expression for the hns as a function of n. And we can pull the 2 out. Okay, so we have 2 into h0 plus, well, h1 is just given by alpha h0. And h2 is given by alpha squared h0. And h3 is given by alpha cube h0, and so on and so forth, minus h0. So as you can see, I can pull out the h0 as well from the first bracket and end up with something like this: 2h0 into 1 plus alpha squared plus, there will be an alpha cubed and so on, minus h0. Okay, so we've sort of reduced this problem, if you like, to calculating this infinite sum. So let's just do it separately. If you've done this in maths, you may well have met this in maths as the sum of a geometric series, but let me repeat the calculation for you. So how do I calculate this, which I'm going to call S for now? Okay, so how do I calculate that S? Well, let me just repeat that S is 1 plus alpha squared plus dot, dot, dot. Okay, therefore, what happens if I multiply both sides by alpha? Well, I get alpha s on the left, and then I have alpha plus alpha squared plus alpha cubed plus dot, 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 dot on the right. Okay, but the right-hand side is almost the same as the original S. It's only missing the 1. So the very first term that we had, the 1 over here. So the left-hand side is simply s minus 1. So we've ended up with an equation like alpha s equals s minus 1. And we can very easily solve it. Okay, we factorize the s and end up with 1 over 1 minus alpha. Okay, so we have solved the problem. So we can go back to our to our total distance traveled, which was h, and conclude that this h is given by 2h naught times 1 over 1 minus alpha, so over 1 minus alpha minus h naught. And tidying this up a bit, we end up with 2h naught minus h naught plus alpha h naught, which gives us just h naught into 1 plus alpha over 1 minus alpha. Okay, so this is the total distance traveled over the entire process. And let's just quickly discuss why is this distance not going to realistically be attained in practice. Well, it will be a bit clearer later when we look at the frequencies of the bounces, but essentially you can intuitively see that the frequency of the bounces will become higher and higher as the number of bounces grows, and that means that this compression that in practice happens when the ball hits the floor, compression and extension, the sort of elastic process, will at some point hit the limit of what it's capable of doing, because it takes a finite non-zero amount of time to compress and extend a real material. And once the frequency goes even higher, high enough that it is not possible for the material to keep up with that frequency, then really we're going to stop having bounces. So at some point the process will be effectively truncated. Okay, so let's go to the next part of this question, which is part C, which is find the time between the nth and n plus first bounces. Show that it can be written as 2t naught e to the minus beta n, and give expressions for t naught and beta. Find the total time spent bouncing in the ideal case. How many bounces does the ball execute in this time? Okay, so okay, the time between nth and n plus first bounces, well, we know already the distance traveled between bounces, and we know, let's think about what happens when the ball is at height hn. It's going to fall to the floor, of course, but because hn is the maximum height after the first bounce, what we know is that when the ball, when the ball is at height hn, it has zero velocity. So at this point, let's say the initial velocity is 0, if you like, meters per second. This is not the right place to write this. So at this point, u is 0 meters per second. So it's going to fall, it's going to fall starting at that speed, and we know that it's just subject to gravity, and we know that the strength of gravity is given by this constant g, which is approximately 9.81 times meters per second squared. So we just apply our Suvert equation, okay? And the Suvert equation says that s, as distance traveled, is equal to, after a time t, is equal to the initial speed, which I called u, times t plus 1/2 at squared, when a is the acceleration, okay? But actually, I know that the acceleration is g in this case, so let me write g instead of a. I forgot the square. And in this case, I also know that u equals 0. So s is just 0 plus 1/2 gt squared. Okay. Well, we know what s is when the ball has reached the floor. So we know that s equals Hn when the ball reaches the floor. So the time that has passed is exactly given by 1/2 gt squared equals Hn. And you probably recognize this formula from before. You end up, okay, so let me call this t, this time, not just t, but Tn, because it's related to the nth bounds. And you end up with the formula Tn equals square root 2Hn over g. Okay, but let's now remember what we knew about Hn. Hn is given by alpha to the n times h0. So we end up with this formula. And let's pull the alpha out of this square root. So I end up with just alpha to the n over 2 times square root 2h0 over g. But if you think about the term with the square root of 2h0 over g, that's just the initial, the time that it took for the ball from the very beginning of the whole process to reach the floor. Okay, so it started at the height h0, and it took exactly square root 2h0 over g to reach the floor. So this, we can just say that Tn, therefore, is just alpha to the n over 2 times t0. So I'm calling this the square root, I'm calling it t0. Okay, so this was just the time from h0 to the floor. And by symmetry now we can say that the ball then will take the same time to travel upwards to that height. So when we think about the total time taken, we want to look, the question asks the time between not only between the nth and n plus first bounces, which we just found, but the total time spent bouncing. Okay, so the total time is given by, well, first t0, of course, and then just twice each of these tn's which we calculated. Okay, so we end up with something which looks a bit similar to what we had before. We have something without a factor of 2 in front, and then an infinite number of things with a factor of 2 after that. So let's just play the exact same trick and say that this is just 2 into t0 plus t1 plus dot dot dot, close brackets, and then we compensate for this by subtracting the t0. Now let's also remember the expression which we found just above of Tn in terms of T0. So according to this formula, T0 is just T0, but T1 is square root of alpha times T0, and T2 is square root of alpha squared times T0, and so on and so forth, minus T0. Okay, so oh, no, I want to erase that. So oops. Okay, so what we've ended up with is that t equals 2 t0, we can factorize the t0, 1 plus square root of alpha plus square root of alpha squared dot, 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 minus t0. And we got some very similar problem to the one before. Okay, so let me just go through this quickly and just say, let's just call square root of alpha, let's do it over here, square root of alpha, let me call it something else, let me call it beta, let's say. So we have just t equals 2 t0 into 1 plus beta squared plus dot 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 minus t0. So we got the exact same problem as we had before, and we can just lift up the solution from there And we now know that this is equal to 2t naught times 1 over 1 minus beta minus t naught. And factorizing the t naught and so on, we get t naught, and then using the common denominator, we get 2 minus 1 plus b. Sorry, I wrote b naught. I wrote beta naught, but that's meaningless. And so we end up with eventually t naught into 1 plus beta over 1 minus beta. But okay, let me just remember again that beta was just square root of a. And this is our final answer. So this is the total time taken throughout the entire process. And if you like, we can also just remember that t naught in terms of h naught was just the square root of 2h naught over g. So this is also a valid answer. Okay. Just to comment very quickly on part D, because I'm afraid there's not much time left for us today. The frequency, we want to calculate the frequency of bouncing heard as a function of bounce number n and also of time tn at the nth bounce. Okay, so this is a very good exercise to do now that you've seen this trick and how to calculate these series by multiplying them by alpha or square root of alpha and so on. Which is a very good exercise for you to try out on your own. But just the simple thing to note here is that we want to know the frequency of bounces. So in other words, that is the inverse of the time taken between any two successive bounces. So that's just going to be 1 over 2 times Tn as we calculated it earlier. So from our calculations just before, we conclude that this is 1 over 2 alpha to the n over 2, if you like, t naught. And then we remember that t naught was square root of 2h naught over g. And for the rest of the exercise, you want to express this as a function of the time tn at the nth bounce, not the time between bounces, but the actual absolute time, what you will see on your stopwatch at the nth bounce. The idea for that, and I'll leave it there, is that Tn is given by T naught plus 2. So earlier on we calculated the total time. So this is just, it's almost the same calculation, but you stop. You don't want to calculate the entire thing. You want to stop at, and then you need to think about the index here. Well, you want to know the time at the nth bounce, so you don't want to count the time between the nth and the nth plus first bounce, so you have to stop at t sub n minus 1. Okay, and the key here is that by the same tricks as in the questions you've already seen today, you can calculate this sum, which this time is not infinite anymore, but by exactly the same tricks, you can calculate it, and then you can plug in your answer into the equation that I've just labeled star to calculate an expression for fn in terms of star, in terms of tn, and not alpha to the n over 2. Okay, just a very quick comment. You would expect that the frequency increases to infinity. Well, if you look at the expression 1 over 2 alpha to the n over 2 t naught, you know that alpha is less than 1, so let's remember that alpha is less than 1. Well, then at the denominator, so this is just 1 over t naught, 2 t naught times 1 over alpha alpha square root of alpha, if you like, to the n. The point is that if alpha is less than 1, then 1 over square root of alpha, so 1 over square root of alpha is actually going to be greater than 1. So you have you have a constant times a number that's greater than 1 to the n. And it's quite clear that if n tends to infinity, this number will tend to infinity. This quantity will tend to infinity. So the frequency will tend to infinity as expected. So thank you very much for participating to this online tutorial. I hope you found it helpful, and keep asking questions and send us emails if there's anything that you find still unclear. And check the events page for our events, and I hope to see you soon. Goodbye.